I don't think I need, yeah, I'm not going to need a calculator anytime soon. So I'll just bring up this on the big screen and we'll just kind of dive right in. And like I said, I'll talk to you a little bit about the scheduling, the next couple of weeks, because in 2 weeks we don't have class because of election day. So so there's that. Next week we have another skills assessment. Right. So that shouldn't be too crazy. And also, I don't know, some people kind of look forward to those days because of the fact that there's no lecture on that night, so you don't have to listen to me droning on for 2.5 hours. Plus, you can do your assessment and be on your way. So it's kind of like once you get over that hurdle, you're done for a couple of weeks. So it's kind of a nice feeling. Right. And then once you come back from the election day break, we'll be in the back nine. We'll be just wrapping up the course, which is kind of hard to believe. It's coming up on November, so we're actually getting there. All right. So we just have some content to get through tonight, and then we'll see where we're at. So, I just kind of introduced the idea of word problems and the fact that it's always going to be an ongoing struggle, and so you want to constantly be reminding your students to read the word problem, draw and label, and then write a number sentence and a statement that matches the story. All right. So there's always that component there, that the idea that you can't just say x plus 2 equals 3 and then x equals 1 and call it a day. If a question is presented in words, the response should be presented in words. So it's all part of that process. Right? And so the students need to be constantly reminded of that at every age level. Right? So from the moment that they're able to start working on math problems, they need to know that these are the expectations. Right? But before they get to a point where they can write, effectively, you kind of make concessions, and it's like, well, we'll take what you can get, anything that gets the idea across. And when we were going through Common Core training back in the day, the New York State gave us a set of exemplars that showed us what acceptable student work would look like. And that acceptable student work, if it were presented to a mathematician, so somebody from the days of Isaac Newton, or Wilhelm Leibniz, that they would be it would be the sort of thing that would be frowned upon. And we're like, this is nonsense, but if it explained the student's thinking in a way that addressed the mathematics, then it was sufficient. So we go from that way of thinking to the formal discussion using appropriate vocabulary and terminology. All right. So when we look at something like the first example, this week, Maria ate 5 yellow plums and some red plums. If she ate 11 plums in all, how many red plums did Maria eat? So this is a pretty typical type of question. It's not something that I made up. It's in like some variation of this is in every textbook. I'll call them textbooks. They're basically the workbooks from Engage New York. So read the word problem, check. Draw and label. Right. So we're talking about an age group here where let statements aren't going to necessarily be a thing. All right. So, like the instincts for us might be to say, let X equal the number of red plums. And then you write the equation and then solve that equation. But that's not going to work for a first grader. Right. So what you do is you get some crayons out and you draw some yellow plums. Honestly, I have no idea what yellow plums look like. So I'm just going to draw yellow dots and hope that people don't have too much experience with yellow plums in order to call me out on the inaccuracy of my diagram. All right. And then some red plums. All right. So we're going to have a selection of red plums. I don't know how many there will be. Oh, that's not my red pen. So I'm going to have some red plums in there. In the end, I'm going to have a total of 11. All right, so I'm going to need to have 11 when all is said and done. So 11 plums. All right, so the student may go about it this way. They say, okay, I got 1, 2, 3, 4, 5. I need to get to 11. All right, 6, 7, 8, 9, 10, 11. All right. So when I put the numbers in there, I'm putting them in as the ordinal values. So the first, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, the 10th, and the 11th. Right. But this collection of plums here amounts to 6 plums. So if we want to get into the concept of addition, all right, we would say, all right, now you got your diagram. That's great. A well-labeled, well-drawn diagram. Right? Mine's enhanced by technology, which it had to be because otherwise it would be disgrace. But what I could say then is, okay, now I got a roadmap, a blueprint, everything good to go. Now I got to get a number sentence going on here. So I can write that in a couple of ways, but my sentence is going to be 5 plus 6 equals 11. But that in particular means that I'm looking at 5 yellow plums plus 6 red plums is going to give 11. Well, we could say, I mean, if we want to go a little, be a little too specific, maybe we could say 11 yellow and red plums, but we'll just say 11 plums. All right. So now we have to answer the question. All right. So all this supporting work, which you didn't necessarily think we would be able to elicit from, well, certainly not from the students, but from this problem. Like, how am I going to pull all this information out from this problem? It's a whole lot of information for not really that complicated of a question. But all of this is getting at the underlying thinking. All right. So what we would say, just to answer the question, Maria ate 6 red plums. All right. You know, it's kind of like a tough battle to fight to get students to want to do it this way. They'll do it this way because you're telling them to do it this way. But to get them to do it this way without you saying, first do this, then do that, then do that, you know, that's a different story altogether, because we've all been in the situation where, you know, you'll learn something and then a period of time goes by, maybe months, maybe years, maybe honestly, maybe hours and days. And then you're expected to recall that information and you say, oh, I knew that at some point. I know it's in there, it's in the old memory banks, but I don't remember it. Right. And so for students, that's an ongoing thing. You know, they're always at a point where they're asked to recall information that they've seen previously, and whether or not they have instant recall on that is a different story. Right. So having them develop this sort of approach, or maybe, you know, it doesn't even have to be specifically this approach. I mean, I'm partial to the way I like to do things, but it, you know, it could be something just, you know, completely native to the way that you like to do things. And if that's the case, then it's more authentic. But it's something that, like they have structure, they can build off of that structure, and they can use that to solve problems down the line. And I had a student today in my freshman algebra class. He was working on an activity. I was using a Desmos activity, right? Somebody just like I was talking about last time, somebody else made it, and I made it quote unquote better. All right. So I took what they started with and I made it better. Did I really make it better? I don't know. I just made it to fit my needs, so I adapted it for my needs. And that's the subject of your technology assignment. So that's a good thing. But as the student was working through it, there was one question where it just said, write the inequality. It was just flat out, write the inequality. So he raised his hand. He asked, do we have to explain our thinking? I said, oh, well, that's a great idea. I wasn't looking for that in this particular case, but he was ready. As a student who had gone through this kind of system, he was ready to have to explain his thinking in order to get full credit for a problem. So the training is paying off. It's just it's a struggle in the early going because we'll blame it on the parents. It's always the parents' fault. They're like, well, we never learned it that way. Why is your teacher teaching it like this? That's usually how it goes. So once we get over that hurdle, then everybody will buy into this approach, and it'll change the whole system. And then everybody will get aggravated that there's a new approach. So, that's education. Anyway, number 2, some children are on a playground, 8 are on the slings, and the rest are playing tag. There are 15 children in all. How many children are playing tag? So, I color coded the last one because it made sense to. I'm not drawing little pictures of little swing sets. I'm not capable of it. Some people are. So what I'll do is I'll use the letter S to represent swings. So I'm just going to draw 8 S's. And I know that I'm going to have a bunch of people playing tag. And that's going to amount, not what I intended. That's going to amount to 15 children. Right. So I know I have 8 people in the sling category. Can't really write the numbers inside, the letter S. So you just kind of make do. But what you could do, you just kind of make little notes here. 1, 2, 3, 4, 5, 6, 7, 8. And for the younger ones, this is a good way to connect cardinal ordinal numbers and application questions. Now I need to get up to 15. So what I can do is I'll use the letter T for tag. So 9, 10, 11, 12, 13, 14, 15. So I'll make little notes, again, just little notes here and there. 9, a little too thick. 10, 11, 12, 13, 14, 15. All right. And so again, that leads us to a result. And in this case, we have 1, 2, 3, 4, 5, 6, 7 individuals playing tag. All right. So when we're formulating our final answer, we would say 8 plus 7 is 15. And that's 8 on the swings plus 7 playing tag, and that's going to be equal to 15 total. All right, kids, for lack of space. All right. So then, just to answer the question, how many children are playing tag? 7 children are playing tag. Right. And that's really all there is to it. It's just kind of building out from what you're given and coming up with an approach that makes sense. Just going to say something else. I just kind of lost my train of thought. I'm sure it was powerful. They'll come back. Tanya has 12 ladybugs. How many more ladybugs does she need in order to have a total of 21 ladybugs? All right. So, we're using addition, but maybe we want to try a different strategy, right? Maybe what I want to do is start off with 21 ladybugs, all right? So let's try a different approach here. I can't draw ladybugs, so that's what we get. All right. So this is a set of 21 ladybugs. She's got 12 of them already. All right. So make a little cutoff here. I'll just make a little note that those are the ones that Tanya has, and then you can count up the ones that are left over. All right. So if you have a certain amount that are left over, that implies subtraction. All right. So what I can do instead, because it's saying how many more, it's not really a question of, what approach to take. It's read the word problem, draw and label, and write a number sentence that matches the story. All right. So I could say here, 21 minus 12 is going to be equal to 9. All right. And then we could verify that by saying, okay, do I have 9? Well, let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, and finally 9. All right. So they're all there. We can get it that way. All right. So, and we could just kind of tag it total, Tanya, and then the lefties, the leftovers. All right. So to answer the question, we would say Tanya needs 9 more ladybugs. So different approach, but same type of question. Lowercase. So yeah, it's just strategizing, deciding which approach you want to use. Yeah, and you could also, when you're asking your students to do this, you could decide, all right, well, I want you to do it using subtraction. I want you to do it using addition. When you're teaching the content, in the context of that content, the students will know, all right, well, we just did a whole worksheet on subtraction. So clearly subtraction is the way that I should be doing this, but they don't all pick up on that. So sometimes you want to be explicit in your instructions when it comes to that. And the younger levels, you always want to be explicit in your instructions. You don't want to take any chances, but when they get a little bit older, you can kind of imply things and they pick up on your implications. All right. So subtraction takes on a bunch of different forms. The two most important ones I would think would be as a basis of comparison, and also as a method of finding displacement. It's just the thing is most kids don't use the word displacement, but they have an intuitive understanding of it. They just don't use the word. All right. So, you know, sometimes it's just a simple matter of saying, you know, let me subtract and see what the difference is between two values in order to determine more, less, equal, different, you know, that kind of thing. Right. So we have Anna has 7 butterflies. Katie has 9 butterflies. I want to know who has more. All right. But it doesn't, we don't want it to just be a simple matter of saying, well, Katie has more because her number is bigger. You know, we want the justification for why the number is bigger. All right. So a diagram, an equation, a verbal statement, sometimes all three, they all go hand in hand here. All right. So I'll just draw a quick diagram. We have Katie and her 9 butterflies. And we have Anna with her 7. So if we want to do a quick side-by-side comparison, what I would say is, all right, well, let's identify the commonality between the two sets. All right. So I'd be saying, all right, 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, 7 and 7, and then we can see that there's 2 left over. Oh, that's a little thick. 2 left over from Katie's set. All right. Now that 2 left over is the same as saying, you know, what you might have intuited from this, that 9 minus 7 is equal to 2. That's where that 2 comes from, but this is the visual representation of that. All right. So we get the idea that Katie has more butterflies because she has more butterflies. You know, it's like common sense, right? Katie has more butterflies because she has 2 butterflies more than, Katie, than Anna has. But in terms of really driving that point home, the diagram is what gets the job done. Right? Because otherwise you don't know that they know it. And that's really what it all comes down to. I think, and I have no research to back this up, so you can take it with a grain of salt, but I think it'll make sense, and you can just kind of choose to believe it or not believe it. It's up to you. But I think that this approach for instruction came into being in a general way for a couple of reasons. One, because teachers were so fixated on their answer keys and whether or not the students' work matched their answer key, right? You got that question wrong. Why? Because you didn't do it the way I did it, right? Yeah, I got X equals 2. You got X equals 2. You did it in a different way. You must have cheated, right? It doesn't matter that you did it in a beautifully articulate, elegant way. You must have cheated because you didn't do it the way I did it, and that's the way we did it in class. You know, there's no possibility that the kid could have just had insight into the way the structure of the problem worked, right? And the other reason is because data, collecting data, and it's like, I remember for a solid decade in the middle of my career. I guess I'm still in the middle of my career, but it feels like I'm kind of at the end. I'm not. I still got like 20 years to go, but I'm going to get off that line of thinking because it's depressing. So for about a 10-year stretch, anybody who watched my classes, observers, you know, because you always have administrators come in the classroom and they ask you questions of like, why did you teach that way? You know, like what was your thinking behind that grouping of students? Why did you put those 2 students together and not those 2 students together? What was your thinking? All right. But the big question that always came up is, how do you know that they, I'll say it in a weird way. How do they know that, how do you know that they know what you wanted them to know? Right? Basically, how do you know that they learned what you intended for them to learn? You know, so, and it is a hell of a question. In a lot of cases, it's like, I don't know. Well, I wouldn't say that out loud. Out loud, I would say, well, because I put together a really thoughtful lesson plan and I crossed the T's and dotted the I's and my presentation was beautiful, like all the material, blah, 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 blah. But how do you know that they know it? Right? How do you know that they understand it? When you have an objective, students will be able to. Like, how do you know that they've achieved that objective? Sometimes it's as simple as, if your objective is solve this equation, sometimes that's easy. You just give them an equation to solve. If they solve it, they've met the objective. If they can't, then they didn't. But students will understand subtraction. Holy crap. I mean, that's a tough one. Students will understand subtraction. How do you gauge that? Well, you don't gauge it by having them do 100 problems, all of subtraction. That's going to tell you that they know how to subtract. How do you gauge their understanding of the concept of subtraction? That's where all this stuff comes into play, right? So that's where the big challenge is. So, you know, if you came up through this system and you're like, why do they make us do it this way? Why do we have to learn 3 different ways to do the same problem? That it's really trying to get at that idea. How do I know that you know what I wanted you to know? Right? Right. So in this case, who has more butterflies? Well, my work will kind of tell the story here, but we do have to answer the question. Katie has more butterflies. Because she has, and it's going to sound like the world's worst, like run-on awkward sentence, but this is what we want, you know, because she has 2 more than Anna. You know, that's a pretty typical answer for what the students would come up with, right? Now, you have different kinds of learners and different kinds of students in the class. Some of them are, you know, more expressive. You know, you ask them for a couple of brief sentences to answer a question, and that their interpretation is, okay, so you want a 3-page paper. And, you know, it's like line after line after line after line. It's like, oh, I got the point, you know. But then a couple other people, you know, other people will interpret brief as brief. You know, the definition of brief means, all right, short and sweet. So what's the answer? Katie has more because I said so. Katie has more because look to the left. Because of the picture that I just drew, you know. So it can get a little tricky. Is there an easy answer for that? Well, yeah, but implementing the easy answer is a little bit of a different story, because, you know, the idea is, like, I mean, everybody's a teacher, right? Everybody in your classroom is a teacher. They have something to offer. So the students who are really expressive and able to articulate their thoughts are your examples for the students who aren't very expressive and are unable to articulate their thoughts. All right, but the challenge is implementing that, because you don't want it to be like you're holding those students up on a pedestal of like, oh, look at this great work here and look at your piece of crap work. You know, like, you don't want it to be like that, but you do want to get across the idea of like, this is what a good answer looks like. This is what a not so good answer looks like. You know, and in the middle, all right, well, let's talk about this one. How could we have made this sentence better? How could, you know, like, what kept this sentence, you know, from being great? It's only okay, it's only good right now, but what kept it from being great? have that conversation with your students, and it does go a long way. Number 5, I don't even know what happened there. That is that's one hell of a typo. That's oof. Yeah, this I have no excuse for this one. I think I just copied and pasted it with the intention of changing it, and then I just never changed it. That's not even a question. I mean, I guess the part of it says who has fewer butterflies, but that's not even, it's not unique. It's the same work as the previous question. So nothing new to the party there. All right. So displacement. Jed takes 11 steps forward, followed by 3 steps back. What's his displacement from the starting position? All right, and justify using a diagram. And diagrams for these kind of questions are pretty straightforward, literally and figuratively. Too thick. So we give him an initial starting position. So here's position 0, and we'll make a note that that's where he's starting. He's going to take 11 steps forward from that spot. All right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, and I wrote 10 for some reason. Of course I have it, I think. All right. So we're calling this direction forward. You can call any direction you want forward. The implication is that the opposite of that would be backwards. All right. So he took 11 steps in the forward direction. Here's him taking a step. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. Those little arrow diagrams there, you know, you don't actually have to use arrow diagrams, but you should have something other than just the number line, something to give the indication of movement along that number line, because that number line does not necessarily mean displacement. You got to think about like a road that's 10 miles long. Just because the road's 10 miles long doesn't mean that I walked 10 miles along that road. Right? That road is just 10 miles long. Maybe I only walked 2 feet along that road. Right? So you want to establish the road and then also the movement along that road. Right? So that's my 11 steps forward. Now I'm going to go in the reverse direction. So I'm going to, well, needs green. So he's at this position. This is now my new start. I'm going to go 1, 2, 3. All right. So those are the 3 steps in the backwards direction. So this way, I'll make a little note backward. All right. And you know what? I'll change my notation here to make it a little bit nicer, or a little bit more consistent, I should say. Yeah, there we go. A little bit more user-friendly. All right. So now we just need that number. That the number at this location is the key to this whole thing. Right. So that's where the ordinality comes into play. So the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and 11th steps. Right. But it's also a position, which gives it a cardinal value. So we're looking at his displacement is going to be 11 minus 3 equals 8 units All right. So this is one of those interesting situations here. And, you know, I'm not going to say that I'm going to put this exact problem on the test, but, or on, sorry, the skills assessment, but I'm totally putting it on the skills assessment. If you want, go ahead and star this problem, because it's going to be a, yeah, I think I'll just let, oh, okay, so Jed will become Ned, I guess. And 11 steps will become 15 steps, and 3 steps will become 5 steps. But, you know, you get the idea, right? So I like this problem in particular because it hits on a whole bunch of problems, a whole bunch of concepts that we've been talking about throughout the course that permeate throughout elementary mathematics, right? So we talked about displacement, all right? That's more of a scientific term, but still, right? We got subtraction. You turn it around, you got addition, right? If you start off with that position 8 and add 3 to it, you get 11, right? So you could think of it that way. But I like the cardinality, ordinality aspect of it, right? And that's because that 8 is both a cardinal number and an ordinal number in this context, right? So 8 is cardinal and ordinal. All right. So it's interesting in that regard. And I'll just make a little note here. It's beyond the scope of the question, but it's kind of nice when this sort of stuff happens, you know, organically in the classroom, because, you know, it's sort of a thing that you'll be surprised that your students pick up on. You know, they're not going to say maybe necessarily the words cardinal and ordinal, but they'll say, oh, wait a minute. So 8 can be a position, but it could also be like a number of steps, right? So this could actually be, you know, in the forward movement, 8 could be the 8th step forward. But it could also be position 8. All right. I'll do some highlighting so that we actually have the right term associated with the right thing. So the cardinal number is the position one. But really, if you think about it in terms of total movement, you know, there's a follow-up question just waiting to be asked here. So you write this whole thing. You have the students do all the work, they come up with the answer, they come up with the 8 units, displacement 8 units. And you follow that up with how many total steps did Jed take? Right? Because he took a total of 11 steps and then 3 more. So he took a total of 14. Right? So in order to get to that position 8, he took a total of 14 steps. You know, it's a question of efficiency. You know, it's like try not to equate everything to sports, but sometimes the first thing that comes into mind. It's like a pop fly in baseball. You know, the outfielder, you know, misjudges it, so accidentally takes a big step backwards, thinking that the ball is going to go over his head, and then realizes, oh, no, it's going to fall in front of me, and then runs as fast as he can to make a diving catch, catches the ball, ends up on Sports Center, looks like this amazing play, when in reality, because he took a negative step, it cost him some of that, you know, that movement, you know, or it added to his displacement, you know. So it's just one of those things where that's a natural anecdote that you could share with the students, and maybe not baseball, but something that that they can relate to, you know. For students, I mean, you can, I see this all the time. I assign IXL work fairly frequently for my my freshmen, because they're still learning the skills. And when you're dealing with elementary grades and all the way up, I'd say ninth grade is probably the last year where IXL is like useful. Nah, that's not fair. You could still get a lot of use out of it afterwards, but where like drilling on a concept is a good thing to do. Because after that, you start having to work towards intuitive understanding, and it's a little bit of a different story. It's a different battle to fight. But I have students that like I'll tell them to complete module I believe it was 03. Told students to complete module 03, and that module consisted of 20 questions. Right. So if you kind of equate it to this example, that's 20 steps towards completion, right? It's like a displacement, so 20 steps toward completion gives you the displacement in the context of completing an IXL assignment, right? So I had a student who's in my ninth grade class, never changed the settings. So he was still in the 8th grade curriculum. So he did half of the assignment 03, module 03, but in the 8th grade curriculum, then realized he was in the wrong course, then changed and started doing the 9th grade work. So that's like taking 10 steps in the negative direction, so he took negative 10 steps because he was working away from completion, not towards completion. So he ended up having to do, let's say, 30 problems in all in order to complete 20 problems that were assigned, right? So that the equivalent of that is if you're running a race against somebody and it's on your marks, get set, go, and you start running in the wrong direction, 10 steps in the wrong direction, turn around, realize, dang it, I'm going the wrong way, and then you start running in the right direction. That's all that wasted movement. Right. So a lot of anecdotes that you could share with your students. Right. So don't be surprised if I ask you to share one of those with me. Come up with one on the fly, maybe as part of the skills assessment. We'll see. Right. Number 7, Tatiana counted 14 frogs. She counted 8 swimming in the pond and the rest sitting on lily pads. Right? How many frogs did you count sitting on lily pads? Solve using the displacement method. Right? So we're going with that same idea that we're working with a number line. So it's kind of weird. It's like how do you involve displacement when you're dealing with just frogs sitting around or swimming? It is the same idea though. Just like when I was saying IXL work could be thought of in terms of displacement, the number of frogs could be thought of in terms of displacement. All right. So we would just think of what do we got? The swimming. Swimming could be movement in the positive direction, and sitting on the lily pads could be movement in the negative direction. So we'll start off with the I just lost my train of thought. The swimming frogs. Right. So, I mean, I guess I could pick up my train of thought just by reading the question again. So 1, 2, 3, 4, 5, 6, 7, 8. All right. So that's the swimming in the pond. And I'll put the numbers here. 1, 2, 3, 4, 6, 7. Oh, geez Louise. 7, 8. All right. Now we got to get to a total of 14. So if we're going with sitting on lily pads as a result to get to 14, we could do it this way. It's a little wishy-washy, but it's still technically correct. Right, so this is the swimmers, and then going the other way, would be the sitters. So I'm at 8. So this is 9, 10, 11, 12, 13, and we get to 14. All right. So this whole idea of displacement, what we would be doing is counting not the position in this case, but movement. All right. So 1, 2, 3, 4, 5, 6, 7, 8. It's a total of 8 on the in the forward movement, and then 1, 2, 3, 4, 5, 6 loops going in the opposite direction. All right, so we get 6 going the other way. All right, so we get our 6 and our 8. We know what we got. We solved it using the displacement method, using a diagram. So then it's a question of, all right, so what does that mean in terms of an expression? Well, we had 14 total movements. Minus the 8 swimmers. So I'll actually annotate here. 14 movements minus 8 in the positive direction is going to give us 6 in the negative direction. Yeah. You could also, I mean, another way of handling it would be to count out to 14 and just start dialing back. So I'll show you another strategy really quickly. This is just the one I just showed you was to just get a count. But if you wanted to, it still uses the number line. It just uses it in a different sort of way. We start off with the 0. We end up with 14. I'll just kind of divvy it all up here. I need that's not going to work. So we can look at it this way and say, all right, well, we're starting off with 14 frogs. So that corresponds in this location. She counted 8 swimmers. Right, so here we would be looking at swimming being a negative quantity. So 1, 2, 3, 4, 5, 6, 7, 8. Right, so this is 8 in the negative direction. Right, and so we kind of, if for lack of a better term, I'll just call it the meet in the middle approach, because if we're looking at everything left over, yeah, it gives us a position of 6, but we would get there by doing 1, 2, 3, 4, 5, 6 movements in the positive direction. Right. So in that regard, we would be looking at 14 minus the 8 gives you a 6, but we wouldn't be looking at these two quantities anymore. Right. So what I can do is I can clean this up a little bit. All right, so here I'd be looking at just position. So position 14 I might as well just erase and rewrite. So then subtract 8 steps. And those steps are corresponding with the swimmers. And then you'll be left with 6. And that's going to be 6 steps, but in the positive direction. And this is corresponding with the sitters. So how many frogs did she count sitting on the lily pad? To answer the actual question, we would want to say she counted 6 frogs sitting on lily pads. Tatiana. Two M's, one M. All right, so she counted 6 frogs sitting on lily pads. Lily has always been like a tongue twister for me. Lily. All right. So next up is our commutative and associative properties. So we have the build to 10 technique that we talked about last time. So I'm going to just kind of refresh your memories on that real quick as soon as I adjust my seat here. So yeah, it was one page ago. So at the top there, the build to 10, take from 10. The idea is to just kind of borrow values from one number, tack it onto the other in order to build to 10. And then whatever's left over, you can combine usually more efficiently and conveniently. All right. So that's what we're going to apply here when dealing with these operations. All right. So let me show you very quickly. We have 4 plus 7. If I want to build to 10, what I would want to be doing here is just snagging some of the 7, a sufficient amount in order to get the 4 up to a 10. All right. So, and look at that and say, okay, well, what do I need in order to make this 4 into a 10? I would need a 6. And then that would leave me with a 1. So it's kind of like factorization is not the right word because that implies multiplication. But if there's a word, and it escapes me at the moment, but values that add to a particular number along the same vein as factors, then that's what we'd be looking at. All right. So let me just see if this is actually going to look, oh, it looks halfway decent. So we get 4 plus 6, and then plus the 1. Oh, it's like writing super tiny. All right, so what we're looking at here is an example of the associative property. All right, so what this is telling me is that I could regroup any way I want as long as I'm following order of operations. All right, so it's telling me that I can take the sum, 4 and 7 is really the same as saying and I'll show the intermediate step, the one I skipped, the one that explains the relationship. This is really the same as saying 4 plus 6 plus 1, but really it's the 6 and 1 that are grouped together in order to give us a 7. All right. So this is equivalent to the original expression on the left-hand side of the equation. But what we're doing is reorganizing so that we can make a 10, a sum of 10, which makes life easier, because then when we're looking at it, we could say 10 plus 1, and now we have our 11. All right. Now, with counting with fingers and everything, you get to 11 pretty easily. Not a big deal, but when you start looking at bigger values, especially for small kids, you know, a strategy like this could be pretty useful. All right. Now, you may also decide that you might want that switching the order on some values, it makes things a little bit more convenient. But that's the commutative property. That one I think kind of doesn't really need too much in the way of explanation. It's really this build to 10 technique that people have historically kind of struggled with. All right, now it's called build to 10, but it's really kind of build to 10, you know, in that you're building to a multiple of 10. It doesn't necessarily have to be 10, right? So what I could do is I could look at the 6 here and say, well, if I want to make that 19 into a 10, all right, well, I don't want to make it literally into a 10. I want to make it into the closest 10, the closest multiple of 10, or tens place, all right? So we're looking at 5 and 1 getting the job done. So this would give us 5 plus 1 plus 19. But again, it's understood that that 5 and 1 was originally grouped together. That's where the 6 was. But I'd be looking at it and say, okay, well, let's move those parentheses around for convenience. This is really the same as saying 5 plus 1 plus 19, which is a whole lot more convenient to work with, because now I'm looking at 5 plus 20, which would give me the 25. All right. But now for a student, you know, you're thinking young ones, you know, first grade, kindergarten, first grade, maybe second grade, depending. 5, starting off with 5 and saying, all right, now give me 20 more on top of that 5. All right. 6, 7, 8, 9, 10, 11, 12, 13. I mean, we know better, but what they would want to be doing is use the commutative property to change the 5 plus 20 into a 20 plus 5. All right. And again, we take yourself out of the adult role. You know, take yourself out of the, oh, I already know this. Why would I even need to do that? You're explaining it to somebody who doesn't really know. Like, they'll sit there, they'll start. If I tell somebody to take 5 plus 100, there are people that will start off with 5 and be like, okay, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, that's 10. 16, 17, 18, 19, 20. Man, it's going to take a while. As opposed to somebody else saying, okay, well, 5 plus 100, that's the same as 100 plus 5. So 100, 101, 2, 3, 4, 5. Oh, it's 105, you know? So one of the biggest adjustments that I had to make when I went from student to teacher, and it happened for everyone, it's the idea that what is like assumed knowledge, in most cases, you can't assume anymore. All right. Like, they just don't know it. They just wouldn't think to do it that way. And so you see a person, and it doesn't matter the age group. You see them working on a problem set that you thought they'd be done with after 5 minutes, and they're still trudging along after 45 minutes. You're like, what's going on? And you look at their work and say, whoa, Nelly, what's going on? Like, we gotta sit down and talk about this, because you're going New York to New Jersey via Canada, so it's probably something to have a conversation over, rather than just saying, okay, well, like, you like doing it your way. I'm sure that's great. Just keep going. I'm sure you'll get it. That's not going to work. Right? So these other problems, the associative property, I just kind of I took care of that. But in the case of the first example, it really is just associative property. It's not really a matter of building to 10 as much as it is saying what kind of association would allow the building to 10 to happen, and not to manufacture it. Right? I could just pull it, pair it up appropriately and say, oh, okay, well, if I put these two together, then I'll get a 10 out of it, and then we're in good shape. Right? So we're looking here and saying 20, I got 13 plus 20. All right. But then another component here, again, you're a kid, you're a child, you don't know any better. You look at this and say, okay, well, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Okay. So that took a while. And you don't want to do it that way. What we can do is manufacture a 10 from the 13. Look at this as 10 and 3. So this whole expression is 10 plus 3 plus 20. Commutative property tells me that I can move some things around here. I can make this 20 plus 10 plus 3. Good for counting. So if you're counting by tens, like, your choices are, if I'm going to add 10 and 90, you want to start with the 90 and tack on a 10. You don't want to start with the 10 and tack on a 90. Right? Same idea with the 10 and 20. Start off with the bigger one and then tack on the smaller stuff. All right. So the 20, then the 30 plus the 3 gives you the 33. All right. This falls in the category of trying to teach common sense, and so common sense is not the right term. It's just for lack of a better term. I mean, we say math sense, but that's, nobody ever truly knows what that means. I'll give you a quick example. One of my uncles, who's really good at golf, we went golfing. And after a round of golf, I was going to add up the scores on the scorecard. Okay, so 18 holes, and some of them, you got a 4 on one hole, I got a 6 on another hole, I got a 3 on a hole, I got like a 9 on another hole. But when it was all over, it was just a matter of adding them all up. And he didn't have much faith in me, because he's trying to tell me, all right, well, you take these two numbers and put them together, then take these two numbers, put them together, and put these two numbers together, and put those together. It's going to make it easier. I was like, listen, I'm a math major. I don't know, like, go away, But what he was trying to tell me, which I already knew, was, all right, I got a 6 on one hole and a 4 on another. I'm not going to add, 3 plus 5 plus 4 plus blah, blah, blah. I'm going to grab the ones that will give me a sum of 10 and just kind of earmark those and say, okay, these are my 10 groups, and then just add the little stragglers at the end. Same thing with mini golf, same idea. You just want to grab the convenient ones. That's all this stuff is trying to teach them. It's doing it in an academic sense, which is, not ideal, but where else are we going to do it? So 6 plus 19, you look at it and say, well, I want to build to the 20, or I want I want to decompose back to the 10. You know, you got different possibilities here. Honestly, I think this might be just a duplication, right? Yeah. So I might as well do it a different way because I accidentally put the same friggin' problem in. So anyway, let's say we did it this way. Break this up to 10 and 9. Okay. So I'm going to purposely overcomplicate it because I did it the easy way already. Okay. So we'd be looking at 6 plus 10 plus 9. But then I can work these two guys to try to build a 10 group. Right. So the 6 could be thought of as 5 and 1. So now what I can do is I can put the 1, let me just circle it in, and the 10 together. All right. So these two numbers together will give me a 10. So this is gone, this is gone, this is gone. They've all been accounted for. So now I'm left with 5 plus 10 plus 10. But by the commutative property, I'd rather write that as 10 plus 10 plus 5, which is going to be equal to 25. All right, so a little bit more roundabout, but the whole idea is to get as many groups of 10 out of this as you possibly can. All right. You could also do it with multiple digits. You know, we did it in some cases, we did it with multiple digits, you know, 2-digit numbers, but we can do it 3 digits, 10-digit numbers, whatever, all sorts of different possibilities. So, you know, the little key ingredient. I feel like everything's a key ingredient, but the concept of nice numbers, we always want to try to incorporate nice numbers wherever possible. 10 is a nice number, 0 is a nice number, hundreds are a nice number, and multiples of 10 are always nice numbers. But then there's some other nice numbers, but it depends on the context. Like if I'm multiplying by 10 is really nice because all I'm doing is tacking on zeros. But if I'm multiplying by 2, that's also nice because I'm doubling. You know, that's not complicated either, right? So what we could do when I'm adding something like 32 and 11, instead of actually adding them, you know, using the algorithm, which we'll talk about in a few minutes, what we do is we take the closest nice number to 32, which is 30. All right. And the closest nice number to 11, which is 10. And we also think about how we got there. Because we don't want, I mean, our answer is not just going to be 40. All right. So what we did was we subtracted the 2 and we subtracted a 1. So we'll have to undo that later on. All right. So we subtracted a 2 and we subtracted a 1. All right. We're going to call this the nice number method. So using this nice number method, what I would get is 30 plus 10 is 40. Now, if I were estimating the sum of 32 and 11, that would be it. This is a good estimation of 32 plus 11. All right, but that's not what we're looking for. We're looking for the actual answer, right? The idea of keeping an equation balanced is going to be an ongoing conversation when it comes to mathematical algorithms. So the balance is anytime you undo something, you got to redo it. If you subtract something, you got to add it back on. You know, like if I tell you that I weigh 200 and I'll be generous, 250 pounds. Right? So I tell you, I weigh 250 pounds, but I really weigh 255 pounds. Then I've introduced an error of 5 pounds. Right? So I'd have to account for that. So if I were to say, all right, well, I know that the real weight is 255, right? So there's the weight that I'm reporting to the world, which is 250, and then the real weight, which is 255. Now, if I tell everybody that I lost 20 pounds, then I would be telling everybody that I'm 230, but my real weight would be 235, right? Because the subtraction would have to be consistent, right? So that's the same idea here. So in order to correct for the fact that we inappropriately subtracted a 2 and a 1, we just add on the 2 and we add on the 1 later on, and we get 43. And this is our actual sum. And I can tell you that this technique is something I use every single day, and not just because I'm a math teacher. All right. Every single day. This is how I add. I mean, if you need to add 2 numbers, I mean, how often are you going to pick up a piece of paper and write out the addition in this form? If anything, you'll take out the calculator on your phone and do it, you know, if you really needed to do it. But if you needed to do it in your head, I would hope that you do something similar to what's happening here. If I say, okay, I'm going to do 55 plus 57. All right, so I know that 55 plus 55 is 110. 57 is 2 more than 55. So I need 2 more than the 110, so 112. You know, so that's how you kind of reason it out. And that's the same idea even for the bigger numbers. If I'm adding 397 and 112, I'd be looking for the nearest nice number to 397, 400. I'd want to be considering how I got there. I added 3 to get there. The nearest nice number to 112 is 110. Right? I had to subtract 2 to get there. Add these 2 bad boys up. So we're looking at 510. Now you can handle the next part of the process, and this is a good estimation of the sum of 397 and 112. And a lot of people are fine with being like, well, 397 and 112, so that's like 400 and 100, a little bit more than 100, so a little bit more than 500. It's usually pretty okay. But if I want to correct for this, I can handle it one of 2 ways. One way would be to say, okay, well, like I did before, undo what I did. Subtract the 3, add the 2. That allows you to use a displacement technique where you say, all right, well, 510 goes down to 507, plus 2 goes up to 509. You do it that way, perfectly fine. A better way of doing it would be to take into account your correction factors. So what do we do here? When we added 3 to the 397 and subtracted 2 from the 112 is, in effect, we are really just adding 1. So this amounts to just an addition of 1. Right? So instead of correcting the 510, all right, so instead of correcting the 510 by subtracting 3 and adding 2, I just have to correct for the fact that I overall subtracted a 1. So now I could just really, added a 1. It's one of those things where you have the answer in your head and you can't help making that part of the question. That's a thing that happens to teachers everywhere. So, or maybe just me, I don't know. So it's a net change of 1. which amounts to a correction value of -1, which gives us the 509 that way. But that takes a little bit more skillful reasoning on the part of the students, right? So that let's just put it this way: you don't lead with that. That's something you work towards. Better yet, that's something that comes from the kids. We're like, couldn't I just, like it's like nails on a chalkboard when students say this. Couldn't I just do that? Couldn't I just do this? You're like, couldn't you just do what? Couldn't you just do your homework? Yeah, you could have just done your homework. Just sit down and look at your plate. Like there's often that component of like, couldn't you just? No, you can't. You're just going to do it the way I told you to do it, right? But if you let them speak and you let them share their thinking and play it by ear, because sometimes like we've all been in the classroom where it's like, oh, I got a better way of doing it, and then they get like half of the explanation out, and all of a sudden you're talking about like their Aunt Sally, and you're like, how did we get here? That I'm not talking about those cases. Sometimes there's a convoluted explanation, but within that explanation is a nugget of wisdom that you can glean and pull from the students. So be on the lookout for that, right? So then looking at number 7, again, using the nice number method, you can look at it as a combo approach, where you might say, well, I got the 67 and the 12. Why don't I take care of that before combining everything else? But if you're really going to stay true to the nice number method, then you'd want to take it all the way from the beginning to the end, at least for the practice. So 328 plus 67 minus 12. You can do it 2 at a time if you want. For your benefit, you probably want to try it both ways so that you can show the students. But when it comes to the subtraction, it can get a little on the trickier side, because the subtraction is really the addition of a negative, right? So what I would do is I'd be looking at this plus, well, it's all plus. So I'd take that down here, make this minus into a negative, and now we're adding 3 terms together, 3 signed numbers, all right? So this is definitely for the older crowd, but it still works with the nice number method, right? So nicest number close to 330. You see it, the answer just comes flying out. 328 is 330. The nicest number, and we got there by adding 2. The nicest number closest to 67 is 70. We got there by adding 3. And the nicest number closest to negative 12 is negative 10. And we got there by adding 2. All right. So that's the tricky part, because with the signed numbers, it's the movement. Like, how do I get from a negative 12 to negative 10? I'm adding 2 to it. All right. So then I can get the sum of these values. And if you want, you could use your commutative property at this point and say, well, instead of adding down the line, why not combine these 2? But you could also just subtract down the line. It really doesn't matter, right? Because we're going to get a 0. 3 plus 7 is 10 minus 1 is 9. And then we get a 3. All right. So you get there. Now what I would also be looking to do is get the net change here. This is the net change of 7. So that's my correction value I want to be undoing that by subtracting 7. All right. So, I mean, it's a nice way to go about solving these problems. It's definitely an attempt to force development of mental math abilities. I think that's probably the best way I could say that. All right, that's what tends to be the case, is that we have to put it on paper in order for the students to, like, answer that question that we need to get the answer to, and that is, how do I know that they're learning what I want them to learn? How do I know that they know what I want them to know? Right. So it goes down on paper, but when the skill is mastered, what ends up happening is, down the line, this ends up becoming part ingrained into their thought processes. All right. So what we'll do now is take a 5-minute break, and then we'll come back and continue on. There's only, I mean, it seems like there's a ton more to do, but if you look ahead in the notes, it goes a lot quicker, because there's a lot more space to do work. But yeah, we'll come back in 5 minutes, and then we'll wrap up this packet, and I'll talk to you about what next week is going to be like. All right. So in the next 2 weeks. And so coming back in a few.